Thank you very much. So I'd like to invite Jim Cowie up here. We had a panel yesterday with the data center, with some of the data center providers from the New York area, or the Mid-Atlantic area, talking about the data center impacts of Hurricane Sandy. Jim is going to come up here with his panelists and talk about the actual, more or less logical impacts of what we saw in Hurricane Sandy. I know there's a graph in one of these slides in here that has the RIPE Atlas information in it. And I was actually stranded in London during Sandy, and I live in the northern New Jersey area, and I got to see when my probe dropped offline in that graph and came back on, and I could tell that my UPS actually lasted for about 4 hours longer than most of the other people in my area. So definitely interesting data. I think that we're going to that we can all learn from in this. So, Jim, you good?
All good.
Are you doing the laptop?
No, okay. Laptop's here for my comfort. Very good. Hey, everybody. We're going to have a great panel here. This is part 2, if you will, of the Superstorm Sandy saga, which started yesterday. Now, what you saw yesterday was really about the very low-level physical support, the people who were really, waist deep in salt water and diesel fuel and urea and whatever. These are the internet researchers, the internet measurement community. They were in their warm offices hundreds or thousands of miles away, probably with a cup of tea. Their power didn't go out. And they were collecting data on this event. So just by way of introduction, I think yesterday you saw a lot of good information about the storm itself, the storm surge, the clouds, the radar, the disasters that befell Manhattan and the surrounding regions. So today we're going to look logically, as Dave said, at the internet and the impact here. Now, it has been said that the internet is the planet's most complex man-made system. I think that that's probably true. And so this was a natural experiment. We're not happy when these things happen, but we do take advantage of them. If you take a big complex system that has billions of people attached to it and 9 layers of abstraction, and you want to find out what will happen if you turn off all the power in one of the biggest cities that exchanges traffic, we would not probably request that anybody try this in reality, but when it does happen, we all spring to action and see what we can see from as many different vantage points as we can. So today you're going to hear a little bit of the fire hose of observation about what happens between diesel fuel and users up top. So as you listen to these guys, be thinking, because we'll have some time for questions, I hope, how could these measurements be useful to me, to you, the network operators? A lot of this will be describing what we saw because we saw it, and if there are ways that this could be useful to the operations community, figuring out ways to respond better, to make these systems more resilient and survivable, we'd like to hear it from you. So our panelists today go in order. We'll start with John Heidemann from the University of Southern California / Information Sciences Institute, followed by Emile Aben from RIPE NCC, not RIS, as I have noted him. RIPE does so many useful things, and I just got the wrong one. We have Doug Madory from Renesys and Patrick Gilmore from Akamai. We'll be talking about the consumer demand stuff. I'm Jim Cowie from Renesys. I head up the research group there. So John, if you'd like to take it away.
Okay, thank you. Hi, so my name is John Heidemann. I'm at University of Southern California Information Sciences Institute. This is joint work with a student and a colleague of mine, Lynn and Yuri. So our question is, what can pings tell us about the degree of outages that happened in Hurricane Sandy? And so in particular, can we tell what happens at the edge of the networks, the customers to the people on the ground? And ultimately, our goal is to understand, can we track, in general, networks across the internet and understand natural disasters and also, unfortunately, understand human disasters, things like Egypt, where things were intentionally shut down, to begin to characterize the difference between long outages and wide outages, that is, outages that affect a few people for a long time versus outages that affect a lot of people for a short time, and to begin to focus not just on routing in the core of the internet, but on the edge of the internet. What happens to people in homes and what happens inside of ISPs? So these are the kind of questions we're trying to look at in this work. So the general approach of our work starts with pings. And so we take a /24, we ping a bunch of addresses in it and watch over time. And basically, our rule is if they're all responding and all of a sudden they stop responding, something happened. And so we look for these bands in this kind of graph. So each bar there is a /24. The green dots represent ping addresses that are responding to ping. There should be 256 of them in this experiment. And when you notice a vertical black bar, that's what we call an outage. So from this, we process this and detect outages for each block, right? The times when things go down. We then simplify this graph and have one line per every /24, and then there's a couple of /24s in the internet, so we cluster them so that the lines that represent similar kinds of behavior get clustered next to each other in our picture, and that ends up with a picture like this. Oh, and then we color them based on geolocation. And so this picture on the bottom right shows you the kind of graphs we can produce. So that green blob in the middle is the results of the Japanese earthquake. You can see there was an earthquake. The dates you can't quite see. The dates go across the x-axis, and the blocks go across the y-axis. And you can see the earthquake took down a bunch of nets, and then they sort of slowly came up after the last couple, over the course of a couple of days. Okay, so that's our experimental methodology. So for the data that I'm going to be talking to you today about Sandy, we're using a sample of 41,000 /24s taken basically randomly, where we probe all addresses in each /24. And basically that results in one probe every 3 seconds to some address in that /24. So that's a fair amount of traffic. That's not something we're comfortable doing to the internet on a whole. And actually work in progress is replacing this very detailed, very complete measurement with something that's much, much lighter weight, about 1% of this traffic rate. We think we can get the kind of results we'll show you with as few as about 15 probes per /24 per hour, something that I think is well below the kind of background noise, 1% of the background traffic that typically is seen by addresses. So the details of the experimental methodology are all in the tech report if you're interested. So let's talk about Sandy. So we were taking a survey of 41,000 /24s when Sandy hit. The data set is listed at the top. When we pare that down, we find 11,000 of those were in the United States. When we pare that down, we find 4,100 of those had enough data that we could look for outages in them. There were enough IP addresses that were responding that we could see this sharp drop when things shut down. We geolocated them using MaxMind, which is not ideal, but what we have. So we geolocated them to states. You can see the map on the right-hand side. 60 of them end up on some unknown location in the United States. So that's that blob floating out in the middle of the Atlantic Ocean. So this is the plot of Sandy. So again, time goes on the x-axis, and networks go on the y-axis, and the networks are all shuffled to make the close ones, things that have outages in common times appear at the same next to each other. And so what you can see, this is in UTC, so Sandy made landfall at midnight, and what you can see is there's a bunch of networks that go offline around shortly after Sandy makes landfall. And you can actually see it takes a while for them to come back. In fact, to try to quantify what we saw, we look at the marginal distribution. So if in each column you sum up how many blocks are down, that tells you the percentage of networks in the United States that are down at that time. And so we'll look at that next. So this graph takes that marginal distribution and blows it up and shows each sample point. So each little red dot is one of our observations, 11 minutes. And what we see is, before Sandy, about 0.02% of the blocks we were observing were down. And that's because, the internet's a big place. There's always somebody doing something. So that's the kind of baseline that we typically see. What happens when Sandy makes landfall is it doubles. And this is looking just at the United States /24s. And so by this claim, we claim that the number of outages doubled in the United States when Sandy made landfall. Now, it's important to say the outages, the absolute rate of outages is still quite small, right? The internet is pretty resilient, and New York is not the entirety of the United States, but a pretty significant uptick in outages. The other neat thing that we can see as we look at this data is we can watch recovery, and you can see the outage rate go back down to baseline, and it takes about 4 days to get back there. So this is nice, but do we really know this is Sandy? And so to answer that question, on the next slide, we looked at our geolocation data and looked at what blocks were down and where were they. And so the light blue values in the middle of this graph are New York and New Jersey. And so from our data, we can see the majority of this uptick is in New York and New Jersey, so consistent with where Sandy made landfall, or / where networks are. Okay, and then this picture actually places the blocks where we see, places the blocks that show outages that we saw. The top 3 pictures are the 3 days before Sandy. The bottom 4 pictures are the 4 days after landfall, and you can see the spike in outages in the New York City area. So it's the same data as on the prior slide, just plotted on a map. So that summarizes the work we're doing. The bottom line is we believe that pings are a very effective tool to judge how the edge networks are going out. They're not perfect, of course, but give us insight into the magnitude of outages and the scope of recovery. We're working to get a deployable system because we're not comfortable putting 3 pings a second into every block in the internet, and we're pretty close to that. And so we're looking forward to being able to track outages internet-wide shortly. The details of our Sandy analysis are in this tech report, which you can get if you're interested. And the data is all publicly available. If you don't believe me, you can go look at the data yourself and tell me where I'm wrong. So I think we're having questions at the end.
Yep, we'll have questions for the end.
Okay, but that's our view from Sandy outages. And who's next?
Very good, Emile. Thanks, John. Very good. There's the
Okay.
screen and timer.
Okay, thank you. So, good morning. My name is Emile Aben from the RIPE NCC, not RIPE RIS. And I'd like to offer the RIPE Atlas perspective on Hurricane Sandy. What did we see with RIPE Atlas? So, for the people who don't know RIPE Atlas, it is a project to measure the internet for the community, by the community, with these real small hardware devices. And so you don't break your back when deploying, and it's really easy. And this is all it is. If you don't have them deployed in your networks already, come talk to me. I'll be here all day, or during the social, or just register at this URL. This is sort of a status update. This is data from yesterday. We have 2,500 hardware devices deployed, 104 countries, roughly 3% of all v4 ASs and 6% of all v6 ASs, and our deployment base is mainly in the RIPE NCC service region. And what we measure is pings, trace routes, which I'll cover in this presentation. We also do DNS, HTTP, SSL, of course v4 and v6, and we do that towards a couple of fixed destinations which are internal to our to the RIPE Atlas infrastructure. So that means all of our probes measure towards these destinations, and these currently are the root servers and data centers where we host some of RIPE Atlas infrastructure. That's 3 currently. And we have user-defined measurements, which is things that a user of RIPE Atlas can define themselves. And the way that goes is that by hosting one of these devices, you actually gain credits, and you can use these credits to make measurements on this whole system. So you give and take from the community resource, as you will. So what the RIPE Atlas team wants from people here, of course, is to use RIPE Atlas, and we want feedback on how to make it even better. And so there I sort of stop my sales pitch by a non-salesperson and get back to what I'm really should be talking about, which is Hurricane Sandy. We produced a couple of RIPE Labs articles, and the URL there points to that. First, we had a couple of RIPE Atlas devices in the affected area. So we could actually see what these devices, how their connectivity was during the outage. So that's not measuring from the outside towards these destinations, but actually measuring from the affected area out to the world. And this actually shows what we saw there. So these are pings from about a dozen RIPE Atlas devices towards a destination in Germany. And every strip chart has the baseline is the minimum RTT that we ever saw for this source and destination pair. And if it goes over, then the RTT increased. So you see degraded performance, or at least for ping measurements. In orange, I marked the Sandy landfall. And as you can see, the top three are New Jersey probes, and they went out for some time. The middle part is in New York City. We had a couple there in data centers that stayed up, but also a couple that went down. And as for a reference, I also plotted the ones in Philadelphia that we had, that all stayed up. So we have a view from the inside to the outside, but we cannot really we don't have enough deployment to actually get very fine granularity on what had an outage, where if you just go from the devices in the affected area. So what I wanted to do next is sort of zoom out to like a macroscopic level and see if we can actually do something more like a seismometer. So where you actually have some kind of a signal during like a natural disaster that shows something about the state of the internet. And actually you can do something like this, or it looks like it, if you look at the changes in path, if you just start counting how much churn there was in the traceroute path. And the way to do that is to look for each source destination pair where you have a traceroute, look at all the IP addresses, and go back in time for, and I took 8 hours, look at all the IP addresses that you saw in traceroute path for this source destination pair, and see if you find a new IP address. And I need these 8 hours to account for load balancing and all kinds of fun things that you network operators do. And what you see then is something like this. This is just counting how many path changes I saw at a given time for trace routes from all the RIPE Atlas probes to 5 destinations in Northern America here. And you can actually see a baseline from below 50 path changes for everybody in the 2 days before Sandy. In orange again is Sandy landfall. And the day after, there was flux, there was churn, there was stuff going on, and it died down after that again. So I think that's pretty cool that you can actually see this from at the traceroute level. A couple of European targets, same thing, but graph is, the absolute amount of churn that we saw is lower because we have less probes deployed in the US, and you can help with that. To make that better. Doing the same trick on the AS level. So we just look at the path and just look what the AS path was that we saw in the trace routes. And we you don't really see a pattern there. So what I think that means is that in the stuff that we measured, most of the churn of the flux of the things that happened in the network were internal to autonomous systems. And of course, the obligatory IPv6 slide, and not the first one of today. In IPv6, we actually see two sharp peaks around midnight UTC of the 30th and the 31st, and that is actually around the time when one major IPv6 transit provider, whose name has something to do with hurricanes, switched path. So, and that maybe tells something about how dominant that player is in that market. Now zooming back into New York a little bit and seeing what do we see with regards to path going through New York. Again, from all the RIPE Atlas probes, and in this case to a single destination in Amsterdam, and just counting the number of paths that go through New York and also the number of paths that go through the Ashburn, Washington area. And what you can see, so New York is in red, Ashburn is in blue here. And what you can see around Sandy landfall is that the amount of path dropped significantly. But also, you can also see that quite a lot of path remained. There was quite a lot of traffic still traversing New York here. And trying to see what that looks like geographically. So using the same data as the same trace routes from the last graph, so all the RIPE Atlas probes towards a single destination in Amsterdam. In this case, it's this orange circle, and all the RIPE Atlas probes in this on this map are the downward pointing triangles, and I colored them based on if they went through New York or not. So the gray ones didn't go through the path, didn't go through New York at all. Red, they moved away from New York City if you compare pre and post Sandy. Blue is they kept going through New York City. And also funny is that there's the greens. That's actually people that before Sandy hit, they didn't go through New York, but after they apparently did. So I don't know how, but I mean, we have lots of vantage points there, so you find these types of effects. And also interesting, I think, is to see that for this destination, up till Australia and Southeast Asia, going to a destination in Amsterdam, that traffic also traversed New York. So stuff happening in New York affects large parts of the world. This is same visualization for a destination in Maryland, the D-route route server. You see the same thing. Some path kept going through New York. Other path moved away from New York. So a couple of things. Paths were noticeably more unstable the day after Sandy landfall. Stuff moved away from New York, but not completely. But the most amazing thing actually is that the internet mostly kept working. So, but there will be a next time. The Mayas were wrong. World didn't end in 2012. So what I'd really like to hear from this audience is how RIPE Atlas can serve you best the next time at the next event. And one idea I actually had based on the panel yesterday is that we could crowdsource having more locations that we probe to. So asking data centers, can you give me an IP address that I can probe, and you give us some information like what data center is this, what AS, and we just put it up on a dashboard and we dedicate, say, 50 RIPE Atlas probes towards that destination, and that will maybe save these data centers some support calls and people asking, is your data center still up? Is your data center still up? And they can just go look at dashboards like that. So that's an idea I had there, and I'd be very interested to hear people's opinions about that now or after the session. So that's it from me. Thank you.
Thanks, Emile. We'll take questions probably at the end. We have, so it's interesting here, you start to see how New York becomes a linchpin, not just for connectivity to New York, but lots of stuff goes through New York. So Doug's next.
Hi, my name is Doug Madory. I'm an analyst with Renesys, and this is going to be our take on the impacts of Superstorm Sandy on global connectivity. So the day after the hurricane, we published a blog detailing routing outages, where they were by state and over time. That's not what I'm going to focus on today, but if that's of interest to you, I refer you to our blog there. Today, I'm going to talk about some of the analysis that we gained out of our using our global traceroute infrastructure. So we have our own servers in about 86 cities around the world that are tracing the entire internet at least one time a day. And from there, we can gain a lot of path knowledge of how traffic is actually passing through providers in the internet. So looking at traces that go into New York, after Sandy made landfall, again, like the other speakers here, we saw a drop-off in connectivity as outages occurred in the New York area. On these slides, I've hand-drawn a little red line to identify where I'm estimating landfall is. Obviously, the hurricane didn't occur at a single time. But just as a frame of reference of where we were in respect to the timing of the hurricane. So it took about more than 7 days for all of our trace routes that we're completing into New York to kind of come back up to the normal rate that we had seen before then. But of course, pings and trace routes into outage networks are going to not complete, so that's not a surprise. What we thought was when I started working on this right after the hurricane, what I thought was a more interesting question might be how did the loss of a critical node of the internet affect traffic going from a non-U.S. place to a non-U.S. place? Because I think people don't always have a good appreciation for how much traffic is going through New York. And so overall, in aggregate, from all those places, we did see a dip in how many traces were traversing New York from outside the U.S. to outside the U.S. and I threw Canada in there as well because they're going to have some similar international transit. So we'll look at a couple examples of this. So one of these is this first one is starting from Chicago, which isn't obviously outside the U.S., but outside the Northeast, certainly outside of New York. So starting in Chicago, heading east towards Europe and Asia, we saw a shift first on the right, or on the left, we see a dip in traces that are going through New York, and we take that missing chunk and look and analyze it on the graph on the right, and here we're seeing what changed in these traces, and so we see a shift from shift away from New York, which is colored blue. The y-axis on the right is latencies to responding targets. The x-axis is time. The real red line is Sandy landfall. So soon after landfall, we see traces shift from New York over to Washington, D.C. On level 3's network. Going in another direction from London back towards the U.S., not ending up in the U.S., but down to Latin America or over to Asia, we saw a different type of profile here. We saw a drop-off in traces going through New York. I think the New York is green here on the right. We see that change over to the London to New York, London to Washington D.C. path. Around November 3rd, we start to see the New York the traces through New York start to come back, and eventually, by the end of this timeline, they've been fully restored. So here's another one starting in Stockholm. Traces through the U.S. Through New York had 3 distinct drop-offs as traffic was shifted out of New York. And so when we look at who accounted for this from that perspective, it was mostly Hurricane Electric shifting from the London to New York path to Paris to Ashburn, Virginia path. NTT is starting in South America, heading up to New York and on to Europe and Asia. We saw a shift away from what we're identifying as a primary link, primary hop, so a couple IPs that we primarily see traces across NTT, across the Atlantic, shifts to a blue, which we're labeling as an alternate, one they hadn't seen before. So some backup link came on to carry the traffic, as well as we saw an Ashburn to Frankfurt link show up, while that's colored gray and maybe a little hard to see. By the way, if there's any operators in the room here that know the background stories of these, it would be interesting to hear. What was so I don't know what data center outage caused some of these shifts, but I'm sure there's a fascinating story for a lot of these. Another quick one. This is Dallas going to India, so there's a couple of dips here of traces that were going through New York. We look at where those traces, what the shift was on the right side. We see that they changed from going through New York across the Atlantic to go to the West Coast and go across the Pacific, and that's colored in green. Staying on Tata for one more example here. This one's a little bit more complex. A lot of the previous stuff, I've tried to choose simple things that are easy to explain. This one's a little bit harder to follow, but bear with me. So these are traces starting from our server in Jeddah, Saudi Arabia on the Red Sea, to Bahrain, specifically Batelco, the incumbent in Bahrain. The little hiccups for Tata that you see here are also here. There's these vertical ovals, maybe a little bit harder to see in this graph. Otherwise, normally from Jeddah to Bahrain, we see 3 bands of hairpinning. The bottom band is hairpinning through Marseille, the middle band is hairpinning through London, and then the upper band is hairpinning through New York. This is just a few hundred miles to get from Jeddah to Bahrain. There actually is a terrestrial cable that goes that path. And Saudi Telecom actually takes this to London, hands it to Tata, and Tata then brings it back to Jeddah, and then goes across the terrestrial path. And then what we noticed was this kind of SeaWorld roller coaster profile here that cropped up later. I don't know that we can be positive that this was a Sandy-related thing, but it affected a lot of traffic that was passing through Tata at the time. And we saw a primary New York link get shunted over to a secondary that seemed to have an enormous amount of either congestion or somehow there was some latency on this. In fact, the hop is, one hop is New York, which we confirmed. The next hop is Bahrain, which we confirmed. So there's obviously some MPLS horror show going on between those the hops to get latencies of over 600 milliseconds. So our conclusions were, as we probably already knew, New York City is a critical node of the internet. From every one of our collectors around the world, we had some story like this of some shift of traffic moving away from New York for things that are not even destined for the northeast of the U.S. In the face of outages, we saw global providers routing around failures fairly seamlessly. In fact, I tried to find better evidence in BGP, and this wasn't a BGP story. There wasn't an AS path story. A lot of this was rerouted internally within the providers, and I think Emile found the same thing. And I think events like these help us understand, better understand how providers handle disruptions and other connectivity challenges, and we learned a lot out of this. Thanks.
Very nice. And so last but not least, certainly, Patrick, tell us about this, ping and trace routes, all very well and good, but let's see some actual users. Let's see some user data.
Hey everybody, I'm Patrick. This is Tigger. Everybody knows Tigger, right? Okay, just checking. So Jim started this whole thing with these guys are internet researchers. He wasn't talking about me. I don't research anything. I mostly go to conferences and drink. But I do have a lot of people at Akamai who do some research, and they look up data about what Akamai serves. We, as you probably know, have a large network of servers all around the world, and we serve lots of traffic to various and sundry people on the internet. So that you understand, this is the exact opposite of what these guys are doing. The rest of these panels are doing things like checking out from outside, seeing if something pings in, seeing if a prefix is up, or seeing if a trace route moves. The only thing I'm going to be showing here is actual traffic that Akamai served to actual end users, so things that were requested. This means that, for instance, if a network provider keeps a prefix up, but all the users are flooded out or out of the movies or anything else, we won't see the traffic. So it's a little harder to tease out exact data, but I think there's something to show here. So, as I said, it's a little hard to see the effects of the exact effects. Sandy was not an atomic event, right? Landfall happened at a certain time, but different networks, different providers, different colos, different houses were affected at different times. In fact, there's actually some effect before Sandy ever made landfall because Con Ed was turning power off proactively. You gotta love it when your electricity provider decides to shut off the power before it accidentally stops. But anyway, to help try and show this, I'm gonna show a bunch of graphs that are 5 days in length so that you can see a day before, the day of, and a couple days after, so you can kind of get an idea of the before and after, see how the effect actually happened. I put a red line through midnight East Coast time, which apparently was a mistake because Sandy made landfall at midnight UTC, but nobody's perfect. Next. There we go. So just a little bit about the graph. The information is on the geography level. So I broke it out by state, or somebody broke it out by state for me. Just to be clear, I didn't actually do this work. I just get to stand up here and talk about the graphs. So we have a bunch of individual states, and we geolocate the IP addresses of the end users reaching the Akamai network. We did not care where the server was that was serving this. So if a server in New Jersey is serving somebody in New York, we use the IP address of the end user in New York as the destination, and that's what the graph is for. I took off the y-axes to protect the guilty, and so my lawyers wouldn't yell at me, but I made sure that all the graphs that are side by side, so if you see two things left and right, they have the same y-axis, so you can see the same scale. There's no change in scale there. There is a change in scale from slide to slide, but all the ones that are next to each other have the exact same scale. Enough details. There's a lot of graphs that I was given. I was all like, do we have any data? And somebody like plastered me this PDF with like hundreds of graphs in it. This is just some of them that I tried to copy and paste. Couldn't even fit it on the slide because it was so many of them, so I just kind of overlapped them. But you can see we have lots of fun data, and we know, lots of things like which verticals of our customers are served in which states and at which time. So I tried to pick out some things that were useful. First thing I did is I took 8 states on the United States East Coast, from Maine down to Virginia. It's a little hard to read the tops there, but the slides will be posted. And you can see the red line, like I said, midnight East Coast, not midnight UTC, but the same idea holds that it's about when Sandy was hitting land. And these 8 states don't show a big difference. Sorry, some of the lines are kind of flat because I had to keep the scale the same, so some of them on the smaller states like New Hampshire doesn't have as much traffic as Massachusetts, so the scale's a little different, but it still shows that there wasn't a whole lot of effect for these 8 states across the U.S. eastern seaboard. But if we drill down a little bit further into just New York and New Jersey, these 2 states, for obvious reasons, were a little harder hit. Traffic is clearly affected. This is, the scale is correct. There's a white line at the bottom that you probably can't see that's 0. And so if you just look, there's essentially each white line is a third of the traffic. So you dropped approximately 30–35% of traffic. And it's a very clear and obvious change. Everything goes down, and it stays that way for days. So I think we found something that says this is more than just prefixes going down or something. There's real end user impact here. Interestingly, some segments of our customers actually increase traffic. I picked out this one. It's called financial services vertical. I don't actually pick which customers go into which vertical, but it's kind of obvious what this is, a bunch of banks and things like that. So the banking customers actually saw more traffic after Sandy hit, at least in New York. In New Jersey, it's not quite clear, but in New York, there's more traffic to financial services after Sandy hit. So was a little confused about that, but I mean, I guess it makes a little bit of sense. New York is very, financial centric. A lot of people are trying to move money, I guess, because there's damage. I don't know, but there are some actual increases here. There were 4 verticals, as we call them, for things that increased. Financial services, I guess you can kind of understand that. Travel, hotel sites, duh, I wonder why that increased, right? It's kind of interesting. Everybody's asleep. Am I too monotone? Hello, hello. Just checking. All right, so hotel sites went up. Sandy hits, a bunch of people go to a hotel site and book a hotel. Who here is surprised by that? Anybody? Anybody? Interestingly, things like travel airplanes were not going up. It still went down. Energy utilities also saw increased traffic. Again, not terribly surprising, right? You're out of electricity, you will go to the website of Con Ed and figure out when it's going to come back, since there's the one who turns you off. There's also a quote-unquote vertical called miscellaneous. I don't know what's in it. Doesn't really matter because it's literally an order of magnitude less traffic than any other vertical. So there's some drips and drabs of little stuff that went up a little bit. But these are the only 4 things that went up after Sandy hit. Everything else, every other thing in our database, everything we could look at, every graph I could find was down. They weren't even. They were clearly just down. So Sandy had an effect on more than just prefixes. I mean, clearly, if people wanted to get to a certain site, like finance, like hotels, like utilities, they could, and they did, but everything else was down. So this actually probably shows, in my opinion, something more than just the power outages, something more than just, the data center offline. This shows the human side of what's going on with Sandy. Because if your iPhone is working, then you can still get to the internet, and you do it for only what's important. And then you find out a hotel, and then you go and pack your stuff and you move. And it doesn't really matter whether or not your prefix is up or whether your traceroute goes through London or not. What matters is that people needed the internet for certain things, and they could still use it, which was really gratifying to me. It gives me warms and fuzzies to know that people who had a real problem could still use the internet, could still do some things that they needed. But then when they didn't need it, they packed up and left. And that's not terribly surprising if you think about it as a person instead of as a computer. So that's really what I draw from the Superstorm effect. And I think that's it.
Awesome. So there you have it. You have 4 perspectives. I guess, you're left looking at it and you say, well, it's as I think we were asking questions yesterday, and we said the power goes out, internet goes down, okay. But overall, once you get beyond the local effects that are documented in the places where people have no power, it's interesting to see how well it did, I think. If this is the worst that global warming can bring us, I say, bring it on. I guess we'll take questions at this point. I'd like to hear any thoughts that you guys might have about the data you've seen here, or if any of the operators would like to stand up courageously, as the gentleman did yesterday, and admit to having swung massive amounts of traffic around the planet, as you saw in the graphs. All right. Please, if you could identify yourself.
Sandy Murphy, Sparta. I have kind of a reverse sort of question about security protections in BGP. I always wonder if the security protections are making things harder to be flexible. So we have many different projects which will send you an alert if your prefix is anomalous behavior, it gets originated by someone else, or the path changes or whatever. I saw in one of the presentations a suggestion that routes that had never been seen before suddenly appeared, and there was a suggestion that this was a backup route. And people build prefix filters on a daily basis. Any sign whatsoever that any of those security protections were hampering the response to the incident?
Interesting. Anybody?
I think that might have been my slide as far as identifying an alternate route, perhaps. Now those were traceroute-based and they weren't routing-based. So as far as a BGP-based alert, or it wouldn't have been one. In fact, the paths often just stay the same, and the rerouting was happening internal to the provider. Actually, in every one of the cases that I've got in this presentation, those were happening internal. So I guess I don't have any evidence, nor am I aware of any, that that those types of security mechanisms were hampering anything.
Okay, interesting, thank you.
Sure. Is there something specific that you were hoping to see in the data?
No, I was hoping for an absence of impact from security protections on, and I asked the question knowing that if the answer turned out bad, it was going to be bad for me. But look,
I think we have an absence of evidence, so
yeah, good.
as far as you
Thanks.
can take that.
So our specific data is end-to-end to try to include that as a possibility that we measure, but I can't distinguish it. But that might be a question to ask the audience, since they presumably know if they were impeded doing their work because of security.
Okay, all right. Thanks.
Dan McGinn.
Oh, sorry. I have a reverse question to you, Sandy. Hope you don't mind. What might actually be interesting is to see from your data, if you send out these alerts, if you saw an increase due to an event like this. I don't know if you looked at that or...
People, yeah, okay. None of the projects I mentioned that do that sort of thing are anything that I run.
Okay.
So it's a various different, you know, there have been lots and lots of NANOG presentations of different projects that have that as a focus. They look at the routing history, they attempt to identify some sort of anomalous behavior and send an alert. RIPE has one?
Yeah, in RIS has one. I didn't look at that data, but yeah, we could look at, I didn't look at it, but I mean, if there's some correlation between an event like this and these alerts, if they're specific to routing security, then that's of course interesting, and then it's sort of an evidence that it does have an effect there.
Right. Okay.
Cool.
Thanks.
Yes.
Dan McGinn, Pure One Networks.
Can you speak a little closer to the mic?
Yelling into this thing.
There we go.
There we go.
Sorry.
Dan McGinn, Pure One Networks. Just to humor the group, I'm one of the operators who was affected by this, and you guys are wondering what happened with some of these networks, so I'll tell a quick little story. We have a presence at 75 Broad and 60 Hudson. 75 Broad was a bit of a nightmare with power issues. When we advertise routes through to our transits, we generally advertise the whole region, not just the city. So even though we knew that 75 Broad was going to be affected, we advertised routes for adjacent cities through transit in 75 Broad. One of the first things that we did was we stopped advertising those routes out of transits in that city, or specifically that data center. We were told repeatedly that we were going to lose power any minute now, which was sort of frustrating. After we basically made that adjustment, we were at the point where we were debating making ISIS metric adjustments, which would sort of avoid sort of the New York high-risk area. We decided that was pretty much not necessary because of the rate of failover being what it is and our topology. The 60 Hudson site basically remained stable. Route advertisements were tweaked slightly just so that we weren't advertising as many prefixes out of that particular location. As a result, we're depending more heavily on POPs in places nearby like Ashburn or Virginia or things like that. The overall results were you could see some pretty staggering traffic shifts on our backbone, and as a result, I'm sure when you guys do all your probes, you'd see the traceroute adjustments have been made, but the actual service impact was something that just due to the robustness of networking technologies, it was really not there, other than when the actual end users lost power. Thank you.
Good observation. I know that when we had, I think it was Doug's plots that showed some of the different colors for different providers or different cities as traffic was swinging. The vertical axis there was latency round trips in milliseconds, and if you noticed, there wasn't a lot of up and down. So, right, even though you were swinging a lot of traffic, the experience of the prefixes at the ends was probably not very different. It's surprising how little these alternative paths, added in terms of RTT boost.
The internet is awesome.
Tell it. Yes.
This is Manish from DHS Cybersecurity Division. One of the questions I had with the panelists is a lot of the data presented here is post-analysis. Now, have you guys learned any insights from your analysis which you're hoping to apply, for example, in an ongoing way, for example, to detect micro outages? Large outages, everybody sees a bump in some form or another, but it's the micro outages which can often be very difficult to spot. And are there any lessons learned from your analysis here that would apply to those?
Well, for one, I'd like to look a little deeper into sort of like path changes, and you can actually mine, from that you get like IP addresses that you can geolocate, or you can do all kinds of fun things where you can actually see stuff it's not technically an outage, but stuff in the middle changing that you not necessarily see otherwise. And that is, I think, something interesting to further look into. And one other thing that we want to do is sort of make stuff more real time. So next time you'll have a dashboard type functionality, hopefully.
John?
So in the data that we presented, we focused on Sandy, which was a macro outage. But I think the other data that we've looked at shows it's very critical that we establish a baseline. How much of the U.S. is down regularly? And I think including micro outages is essential in that. And in fact, a really important question for the operator community is there any insight into sub-routable prefix outages that you can share? Because, I have data and I have estimates, and I know how I compute them, I believe them, but the extensive analysis over the last 15 years on routable prefixes, we don't have an analog to that when you get to smaller outages. Yet we know, as examples, just the last speaker, that there is stuff that happens inside of ISPs. And I'd love to get better visibility into that.
I might add one. Did you want to?
So essentially what you're saying is some ground truth validation would be very helpful.
Yeah, and I don't know how to get that other than from you guys.
I just add one comment there. So, we did our initial blog on the impacts. We actually do have a continuous, identification of outages. Most of these are routing outages, but we can do this for traceroute as well. I think when you get to, I don't know how specific you're thinking of micro, but if it's a single IP that was responding yesterday and is not responding today, it's a little hard to make a conclusion that there's an outage or this thing was turned off. There's a lot of things that could happen. The conclusion gets stronger as you see a larger impact across maybe across a whole provider or across a series of providers in the same geography. Then things there's more evidence to go off of. We log these things as they are happening, and so that's how we were able to be able to report on it hours after the event.
So there's one other thread I wanted to pick up. So you mentioned most of what was presented was post facto analysis. I think that's true across the board, right? It certainly took us about a month to pull together the data analysis. I think a key challenge going forward is, can we get to the point where we can provide the kind of analysis that you saw in much closer to real time? And I could imagine 15-minute delay or so, and start to use this not just as a what happened story, but start to use this as a what is happening, and where should we send the fuel trucks?
Nice. Yes, sir.
Brian Dixon, VeriSign Labs. At a previous job, I was involved in a carrier that used a lot of satellite, and just go into the latency that was seen. When you go geosynchronous, you expect each direction to add 280 milliseconds, so you would expect if there's a bidirectional round trip time, it would jump at about 560 milliseconds, so you're probably seeing the satellite. Just FYI.
Okay. We do see satellite. In fact, I've got a lightning talk we're going to talk about this afternoon with includes some satellite analysis of latencies, and you'll see the same observation you just said. I've got included in there, but yeah, it could be satellite. That's true. So I don't know.
Good. I think we have reached the. Oh, we've got one more question. Sure.
Dave Swanson with Windstream. We had a pretty sizable presence in Lower Manhattan that day, and I guess to kind of answer some of the questions about seeing the traffic shifts, we had to move a lot of traffic from like a counterclockwise path over to a clockwise path due to, you know, losing 75 Broad and losing the particular paths going in that direction. So a lot of the anomalies, I guess you would have seen where not necessarily unreachable prefixes would have occurred, but you would have seen a spike in latency and then a drop, could have been attributed to things like that. That was stuff that I ran into directly that day, where I'd have to pull traffic off this route over here on the right and move it to this path on the left, where the end result was the same, but it definitely made some stuff blip in the process.
So what's the clockwise, counterclockwise? Is that just the layout?
Just basically a ring. You know, you'd have a ring that would go a couple hundred miles this direction versus a ring that would go a couple hundred miles that direction. So there was a lot of shifts like that took place that day, at least on my network.
Good. Thanks for that. I think, you know, all of us. Oh, so go.
So a question for the audience. So we've heard a lot about the heroic efforts at tweaking routing to keep things up and to get transit traffic, and we saw some of the impact of that. I was curious if you guys have any comments or war stories for those of you who have end user customers, because if the CO is down, no amount of rerouting is going to get those bits through, or if the end user doesn't have power. I'm curious if you had feedback from your customers about that, or if any of you measured that.
Seems good.
Maybe we'll take it offline.
We may take it offline in the interest of getting you to coffee. Find all of us at coffee and tell us your deepest, darkest stories about this. This really does work best when you match internet measurement with objective reality from the operators. So thank the panel with me.
Just a couple quick notes before we go to break. First of all, surveys. As we always mention, right, you tell us what you want to see more of, what you want to see less of. Is Sean Stewart in the room? Sean Stewart. Back there? I believe they have them in the back. You're the winner of a 16 gig iPad mini for your survey response. What? From iXReach. And we'll have 2 more of them to give away for this afternoon survey and also for tomorrow. So please fill them out. Fantastic prize, again, donated by iXReach. We're going to come back right around 11:30, and we also have the Aaron track this afternoon, so those of you who are interested in giving your feedback, we request that you attend that. Thanks.